So this is once again a classic problem, stationary complex Gaussian processes. And I want to go over some results which are quoted more often, but proof is hard to get by. So to start with, you have a complex Gaussian process. We mean it's I'm going to write it as x of t minus j of t because I want to also write this as using the magnitude. So if I put a minus here, then so x of t and y of t are the real and imaginary parts, and r of t and theta of t are the magnitude and phase. So we know the relations. R of t is square root of x squared t plus y squared t, and theta of t is a tan inverse of let's say y of t over x of t. So everything is a process because we have what we mean by Gaussian is that the real and imaginary parts are Gaussian processes, zero mean Gaussian processes. But a little more is to make it more specific in terms of, so let me look at so first of all it is stationary, so their autocorrelation function depends only on their difference of time lags. So I take two time instants, t1 and t and t plus tau. So first assumption is that x of t is stationary, and similarly we can also, I'm going to write this as so remember, any autocorrelation function has the property that rxx tau is less than or equal to rxx0. This I'm going to call it sigma squared. So I'm going to use this notation. So this rho tau is also symmetric. So rho tau is rho of minus tau because this is a real function. And the key assumption is that the y of t also has the same autocorrelation function. That's what I meant by the special relations. And similarly, if you look at the output, the cross correlation function, or before that we could look at actually the autocorrelation function of the z of zt. So that's expected value of zt z t plus tau with a star. So if I substitute for x of t minus j y of t multiplied by x of t plus tau plus j y of t plus tau and simplify this, this will turn out to be, you can see from here, rxx tau minus j squared, that's plus ryy tau. Then expected value of x of t y of t plus tau plus expected value of y of t x of t plus tau. This is with a minus sign here. So this is rxy tau. Notice that this is the same as ryx minus tau, and this is minus ryx tau. So which is the same as this term. If you write it the other way, it becomes, you can write this second term in terms of rxy. In other words, put this term here. So this is rxy minus tau. So I'm going to make the assumption that this is an odd function. so that these two terms, this difference becomes 2 times the Rxy tau. So that's the two assumptions being made. One assumption is already here, and the second assumption is that Rxy tau is going to be written as minus Rxy minus tau, or Rxy minus tau is minus of Rxy tau, which means this would turn out to be 2 times Rxx tau plus j Rxy tau. So this is the special assumption being made. And I also want to write Rxy tau in terms of, pull out the sigma squared. Whatever is remaining, I'm going to call it as R tau, because again from Schwarz inequality, Rxy tau is Rxy tau also is less than or equal to Rxx 0 multiplied by Ryy 0 square root. But each of them are equal to sigma squared, so that's true. So this is like the correlation function. But one observation from the this line is that, so this means if you put tau equal to 0, you have Rxy 0 is minus Rxy 0. That means expected value of x of t multiplied by y of t is 0 for any particular t. But x and y are jointly Gaussian, 0 mean, so that means their correlation function is 0. That means x of t and y of t are independent. So this is what it is. So if I take the time instant t and I define x1 to be x of t1 and y1 to be y of t, then these two are independent. We just saw that. But if I take an extra time instant t2, or let's say t plus tau, and I define x2 to be x plus and y2 to be yt plus tau, these are also independent by the same argument. So for any fixed time instant, the real and imaginary parts are independent. That doesn't mean y1 and x2 or x1 and x1 and y2 etc. are independent. They are not. So this is where we start actually. So we have from this odd property, we also have, of course, this also means that R0 is 0. It's the same as this property. Remember, R is the normalized correlation between x and y. So let me define, what we are interested is to find the joint density function of these 4 random variables. And we can also, at the same time, we also can generate 2 random variables, R1 and theta 1 here, R2 and theta 2. R1 and R2 being related in this manner. R1 is the magnitude, theta is the phase. And then we want actually we want the joint density function of R theta. So in other words, R1, R2, theta 1, theta 2. And we may want also the joint density function of R1 and R2 and the joint density function of theta 1 and theta 2. And more interestingly, from here, we want to look at the correlation between R1 and R2. And this is a classic result, and this is what I'm going to derive. So to find this joint density function, once again, if you look at the autocorrelation function of Rxx and Ryy, that's sigma squared rho tau, and Rxy, the cross correlation function is in terms of gamma tau. So I'm going to quickly sketch the results. So I start with this vector. We have 4 random variables here, x1, y1, x2, y2. So we want the autocorrelation function of expected value of xx transpose. Notice that all these are, so this corresponds to time instant t1. This corresponds to a later time t plus tau or t2. And everything is real random variables. And if you, so you can use these functions to compute the, so autocorrelation function will turn out to be, I'll write it down here. So this will turn out to be the, remember this, this rho function is going to be rho at tau. Tau is the difference between t1 and t2. This is t1, this is t2. T2 is t plus tau. So the determinant, if you do this quickly, determinant will turn out to be sigma 8 multiplied by 1 minus rho squared minus r squared. And I'm going to write this as sigma 8 multiplied by 1 minus standard notation k squared tau, where k squared tau is rho squared tau plus gamma squared tau. So notice that this has to be less than 1 because this is greater than 0. If these random variables are not completely dependent, then the determinant is going to be positive, and consequently that's less than 1. So we need R inverse. The inverse is going to be 1 over sigma squared 1 minus k squared. When I say k squared, it's actually I mean k squared tau. Then it's going to be 1, 0. You can do it. I did it. Again, this is actually a standard result. So nothing new here, except all the details are generally hard to find. So this will turn out to be R inverse. And now we are, once with the R inverse, we are ready to write down the joint density function of x1, y1, x2, y2, which will turn out to be 1 over 2 pi squared r to the power half. This is a standard expression, x squared r inverse x divided by 2. So this is the reason I wanted R inverse. So we take this R inverse, plug it in here. The determinant is here, we plug this in here. So I'm going to write down the result. So this is will turn out to be all right, there is nothing to it except that you just have to do it. So you take this x vector, multiply it from the left, multiply it from the right, simplify, you will get this much term. So now I'm going to make a transformation to the r theta domain. So I'm going to define x1 to be r1 cos theta 1, x2 to be y1, I guess. Y1 to be, then y1 will be r1 sin theta 1. And similarly, x2 is r2 cos theta 2, y2 is r2 sin theta 2. As you know, the Jacobian, if you do this, will turn out to be simply r1 r2. So I'm not going to r1 r2. So the joint density function of the same density function, but now expressed in terms of r1 r2 theta 1 theta 2 would be 1 over this Jacobian multiplied by the density function. You start substituting these values for r1 and x1. Okay. So if you do that, you can clearly follow it. So you have an r1 r2 because of the Jacobian. Then you have a 2 pi squared sigma 4 1 minus k squared. Notice that this is r1 squared plus r2 squared. So e to the power minus 1 over. So the numerator is going to be r1 squared plus r2 squared minus 2 r1 r2 rho cos theta 1 minus theta 2 by substituting here plus r sin theta 1 minus theta 2. This you can find the whole thing divided by 2 sigma squared multiplied by 1 minus k squared. Of course, k squared is a function of tau. So I'm going to copy this to that board, except I'm going to make one more simplification because I can multiply and divide by square root of rho squared by gamma r squared and rewrite this as so we get in this fashion r theta r1 theta r2 theta 1 theta 2 to be r1 r2 All right, so because I have divided there by square root of rho squared plus sigma squared, but that's k. Remember, k of tau is square root of rho squared plus gamma squared. And theta naught is, of course, a tan inverse of r tau over k tau, over rho tau. So from here, the next job is to find the joint density function of R1 and R2. That's easy because you just have to integrate out over theta 1 and theta 2. So we can pull out the terms. Remember, theta 1 and theta 2 is only involves on this term. So you can clearly see that this can be written as R1, R2, 2 pi squared, sigma 4, 1 minus k squared, e to the power R1 squared plus R2 squared over 2 sigma squared, 1 minus k squared. So we can write this as, I'm going to take this 1 over 2 pi and write this here. So 1 over 2 pi, two integrals, right? So 0 to 2 pi d theta 2 and 1 over 2 pi integral from 0 to pi, the remaining term. So the remaining term is going to be from here. So minus minus plus 2 cancel. So e raised to r1 r2 k over sigma squared 1 minus k squared cosine theta 1 minus theta 2 minus phi naught d theta 1. But as you can see, this is going to be, this is simply the Bessel function of 0th order evaluated at this point, this whole thing. So this is going to be because this is when theta 1 is the variable, theta 2 and phi naught are constant. So we can simply redo this by changing this variable still over one complete cycle. So this will be I naught of r1 r2 k over sigma squared multiplied by 1 minus k squared. And if I substitute the remaining term, so this is going to be simply r1 r2 sigma 4 multiplied by 1 minus k squared e to the power minus r1 squared plus r2 squared over 1 minus 2 sigma squared 1 minus k squared multiplied by I naught of r1 r2 k of tau over sigma squared 1 minus k squared is the density function for r1, of course positive, r2 positive. This is the joint density function for r1 and r2. As we know, r1 and r2 are both separately, they are Rayleigh. So this is actually the correlated Rayleigh, two correlated Rayleigh random variables. So the question is, how much is the correlation between R1 and R2? That's where we are going to go. So this is the correlated Rayleigh two random variables R1 and R2 which are correlated. And actually we know since R1 is square root of x squared plus y squared, x and y are identical, zero mean equal variance, and they are independent. R1, R2 are separately Rayleigh. So this is their, so that means if you work out for R1, will turn out to be R1 over sigma squared e raised to minus R1 squared over 2 sigma squared. And R2 same thing. So on the other hand, I naught of A, as I said before, is 1 over 2 pi integral 0 to 2 pi e raised to A cos theta d theta. This, if you expand simply as a summation and do the integration on the cosine, this is easy to show. This will turn out to be k equal to 0 through infinity a to the power 2n over 2 to the power 2n over n factorial on n. This is actually n factorial squared. This is a standard expression. The way you do this is you expand this, and so notice that there will be terms of the form cos to the power theta to the power n, and that is a standard integral over n factorial. So when you substitute that, you will get this term. And notice that this is an even function of only even powers are retained. So if I substitute this for here, so let me substitute this expression. So this will now read R1 R2 over sigma 4 1 minus k squared e raised to minus R1 squared plus R2 squared over 2 sigma squared 1 minus k squared. And I'm going to substitute for the I0 function. So this is n equal to 0 through infinity, a to the power 2n. So this is R1 to the power 2n, R2 to the power 2n, k to the power 2n over sigma squared 1 minus k squared to the power 2n and 1 over n factorial squared, I guess. And we have a 2 to the power, so 2 to the power 2n in the denominator. So we can use this expression to find out so if you want to write it a little more reasonable, notice that let me, rather than write it one more line, let me rewrite it in this manner. So that's going to be R1 squared over 2 sigma squared 1 minus k squared because we had 2 to the power 2 and all the terms we'll see are here, R2 squared 2 sigma squared 1 minus k squared all right, so we had R1 to the power 2n, which is here, and 2 to the power 2n I have absorbed here, 2 to the power n here, 2 to the power n here, and all the other terms are there. K, so all right, so what we need now is use this expression and find out, this is what we want to find out. We want to find out expected value of R1, R2. Remember, R1 is R evaluated at t, R2 is or the magnitude evaluated at t plus tau. So we are trying to find out the correlation between these two random variables. This is the joint density function. So if we can do this, this is simply R1, R2, FR, R1, R2, dr1, dr2, 0 to infinity, 0 to infinity. So for this density function, we substitute this here. So then this is going to read, so I'm going to pull out the summation outside, summation n equal to 0 through infinity. And so this R1, R2 multiplied by R1, R2, so this reads now, I'm going to write down the results of what I have here. R1 squared, R2 squared, sigma 4, 1 minus k squared. So e to the power this term next. So that's R1 squared plus R2 squared over 2 sigma squared multiplied by 1 minus k squared. Then you have these terms. So R1 squared to the power 2 sigma squared 1 minus k squared to the power n, R2 squared over 2 sigma squared 1 minus k squared to the power n, then k to the power 2n. Remember, k is a function of tau. over n factorial squared. So what is missing here is the integration. So integration is on R1 and R2, two integrals from 0 to infinity. dr1, dr2. So let me tell you the substitution to be done. So obviously you just substitute, this is obvious, one variable u, another variable v, and here onwards, and if you, so of course, then you notice that this will become u to the power n, this will become v to the power n, but du is going to be r1 dr1, so you have one r1 here, r1 dr1 is there, but one r2 will be remaining there. So if you look at all this, the expected value of r1, r2 will turn out to be, so the next step will be n equal to 0 through infinity, double integral 0 through infinity, 2 sigma squared 1 minus k squared over sigma 4 1 minus k squared, u to the power half, v to the power half. This is coming from here because we pick up r1, r2 will remain here. One r1 dr1 will give you du. So still there will be, so this is e raised to u plus v. That's this term. Because u is r1 squared over 2 sigma squared multiplied by 1 plus k squared. So that's simply u plus v. Then you have un, vn, du, dv. Then you have k squared tau over n factorial squared. And here, of course, you have sigma squared multiplied by 1 minus k squared, same thing here, sigma squared multiplied by 1 minus k squared, because look at here, r1 dr1 is going to be 2 cancels, sigma squared multiplied by 1 minus k squared du, etc. So this, if you simplify, I'll write down the next simplified line. So this is 2 sigma squared 1 minus k squared, the whole squared, summation n equal to 0 through infinity, k to the power 2n over n factorial squared. Now the integrals become separate, u to the power n plus half e raised to minus u du. This is v to the power n plus half e raised to minus v dv. But each of those integrals are gamma functions. So this, of course, will be, you can just work it out. This will turn out to be n plus half and then n minus half, etc. up to 3 by 2 multiplied by gamma half, which is square root of pi over 2. And consequently, we are almost there. This quantity will now be two sigma squared 1 minus k squared, the whole squared, multiplied by summation n equal to 0 through infinity. This term repeats twice. This also, the answer is the same. So this will be 3 by 2, then 5 by 2, etc. up to n minus half multiplied by n plus half. This thing squared. Then you have the n factorial 2 times. Then you have k to the power 2n Then you have pi by 4. But this whole thing, so pi by 4 multiplies as pi by 2 sigma squared 1 minus k squared, the whole squared. And this is the definition of hypergeometric function evaluated at 3 by 2 comma 3 by 2, then 1 comma k squared tau. So that's one expression, but we can further simplify this. So what is hypergeometric function? If you look at the hypergeometric function for alpha, beta, semicolon, gamma, semicolon, some constant k, it's k squared, it's precisely this is the expansion. You start with alpha, alpha plus 1, etc. up to n terms. Then you do with beta, but alpha and beta are the same here, so you get the square. And in the denominator you have 1 plus 2, 3, etc. up to n. That's n factorial. And we had the n factorial, and then another n factorial, because that's part of the hypergeometric function. So we took care of alpha, beta, and this 1. And k squared to the power 2n is the definition, and this is a constant outside. So this is one expression. Okay, so we can complete this by, so once again, that's what we have, the correlation between R1 and R2, we had it in this form. And if we can make use of just one standard relation in the hypergeometric function of alpha, beta, gamma, c is also, you have this relation, 1 minus c to the power gamma minus alpha minus beta, gamma minus beta, gamma minus alpha, gamma c. So if you use this, if you apply this relation here, you can quickly see that it comes up to this. Now what is interesting, the final thing is to relate this to a result due to Uhlenbeck from, I think, in the 50s or something. So this gets related to the elliptic functions, and that's where I want to stop by just stating that result. As you may know, there are two kinds of elliptic functions. This is the elliptic function of the first kind. And this is the elliptic function of the second kind, integral 0 to pi by 2 square root of 1 minus k squared tau sine squared tau theta. Now, this result can be written in terms of this. The easiest way is expand everything as a series summation. And so I'm just going to state the results. It's too many terms to show here. So the interesting thing is you can show that the first, can be written as pi by 2 multiplied by 1 plus half the whole squared, k squared, then 1, 3, 2, 4 squared k4 plus etc. That's the expansion there. Here it's going to be, so in general, if you want to write this, so I'll write this. We can write this as summation, 1 plus summation n equal to 1 through infinity, the whole thing pi by 2 outside, then 1, 3, 5, etc., 2n minus 1, here 2, 4, 6, etc., up to 2n, the whole thing squared k to the power 2n. That's the first hypergeometric function. So I'm going to call this 2. And if you bring in the second hypergeometric function, this is the first elliptic function, and the second elliptic function of the second kind is 1 minus k squared sine squared theta d theta. And this also has a similar expansion. Easiest way is just to expand this as a binomial expansion and then again substitute the values for integral sine to the power 2m theta d theta, you will get this expression. So this term is the same as here, except that here there is a denominator, it's the 2n minus 1. And then the whole thing squared. So let me call this 3. And one can also expand this 1 as a series summation. So we already have so this, if you simply use the definition of the hypergeometric summation, for example, this will be 1 plus the minus half, the first term, multiplied by minus half plus 1 plus etc. minus half plus n minus 1, last term. This is twice from here, 2 times. Denominator is n factorial, k to the power 2n. There is a summation here, 1 plus summation n equal to 1 through infinity. If you rearrange, I'm going to leave the details here. This will turn out to be n equal to 1 through infinity, 1, 3, 5, etc., 2n minus 1. Same as there, 2, 4, 6, etc., 2n. The whole thing squared to the power k squared, k tau to the power n over 2n minus 1, the whole squared. And here is the interesting thing. Now, if so you have 3 series in front of you. One is this series number 1, and 2 and 3. So if you manipulate this, which it's easy to show the following result. So this will so this will come out to be E R1 R2 will come out to be sigma squared. So you can write this series in terms of these 2 series. So this will turn out to be, so we have this whole thing multiplied by pi by 2 multiplied by sigma squared. Here, this is equal to, and notice that these things also have pi by 2 multiplied by sigma squared. So if you substitute all this, this will turn out to be sigma squared multiplied by 2ek squared. This is the second elliptic integral, minus 1 minus k squared multiplied by the first elliptic integral. So I'm going to rewrite it here. So that's the interesting result, and I believe this result is due to, this particular relation is due to Uhlenbeck. So remember, R1 is R of t, this is R of t plus tau. So of course this is coming from a Whiteson stationary process. The whole thing is in terms of tau, and if you want, so this is the in terms of the first and the second elliptic integrals. Otherwise, you have the power series expansion there. So finally, I just want to make one point that if you find the correlation between correlation coefficient between R1 and R2, that will be of course E R1 R2 minus E R1 E R2 over square root of the variance of R1 and variance of R2. So this will turn out to be because the variance is for Rayleigh, so you substitute that, so the expression will turn out to be exact expression is like this. All right, so this is again a series expansion, but the interesting thing to see is, remember, if you recall earlier from the joint density function, if k squared tau was, of course, rho squared tau plus gamma squared tau. So this is k squared. So if you had substituted the and the joint density function turned out to be what? Something like this. So notice that if the two random variables are independent, in other words, if k is 0, you can see from here R1 and R2 are independent. Because if k is 0, this splits up, this is 1. So so if the two random variables are independent, of course you can, so it goes both the ways, that's the whole point. If the two random variables are independent, then k is 0. Conversely, if the correlation is 0, you can see correlation is 0 means k has to be 0, k tau is 0, and k tau equal to 0 means rho and gamma are zeros. So if you go back, you can clearly see that from here you will also get this to be fr1 multiplied by fr2. The moral of the story is, if the two random variables are independent, then k is 0. But conversely, if they are uncorrelated, then k is 0, and conversely, and the two random variables are independent. So here is the joint density function when they are not independent. So in general, this is not true. This is the joint density function, and k is this quantity, which is like a correlation function. And the correlation between R1 and R2 can be expressed in terms of k, but it's an infinite series. And if you want just the correlation between R1 and R2, not the correlation coefficient, just expected value of R1, R2, that also can be expressed in terms of the elliptic integrals of both of the first kind and second kind. So here is a communication problem where it involves the elliptic functions, and that's what I thought the derivation will be interesting. Thank you. So this is just to summarize what we have seen so far for stationary Gaussian processes. I've sort of summarized the results here. So you have a complex Gaussian process. The real and imaginary parts are independent at any instant t, and they are also Gaussian with the zero mean and equal variance. Then this is the amplitude. Amplitude is Rayleigh, and the phase is uniform. And except now we look at another time instance, so you have another amplitude. This is Rayleigh. But what we are interested in is the joint distribution between RT and RT plus tau. So if I define R of t to be R1 and R of t plus tau to be R2, we want the joint distribution and also the correlation. We already in the previously we have just shown that the joint density function is given by this expression. Notice that quickly you have R1, R2 term, then the exponential terms, and also this I naught, the Bessel function term. I naught of x, by the way, is integral 1 over one cycle, 1 over 2 pi 0 to 2 pi, or the cosine will, it's just the equally, or it being symmetric, it's also, you can do it over half cycle, 0 to pi e raised to x cos theta d theta. If you make a slight change of variable, you can write it in terms of sine theta over an even region. And then you expand it as e raised to e raised to k over k factorial. But then notice that all the odd order terms will vanish because sine 2 to the power odd order terms are over minus pi by 2 to plus by 2, 0. So only the even terms are maintained. That is 2 times 0 to pi by 2. But this is the integral of 0 to pi by 2 sine 2 and theta is well known. That's this expression. So if you substitute, it's a classic expression for I naught. I substitute that I naught here. If you want, you can also write down the joint density function in this manner. Now this is the expression we are going to use to find out the correlation between R1 and R2. So we substitute this density function here. We simplify this. So I expand the I naught term using the summation and so separate it out as in terms of R1 squared and R2 squared. I call this whole quantity to be U, this to be V. So U is going to be, so we get for R1 squared is going to be U multiplied by 2 sigma squared 1 minus k squared. If you make the substitution, you will get two separable integrals. And this, of course, you can keep integrating by parts. You come up with this expression. So the interesting thing to note is this is again this is the correlation between R1 and R2. So interesting part to notice is that there is a square here. We had this expression before. I just want to go over one simplification, at least in show all the key steps. So notice that these two terms are identical. So the terms are identical. So you can write this squared, in fact. Now the interesting thing is this last term can be written in terms of hypergeometric series. So hypergeometric series of alpha, beta, colon, gamma, colon C is alpha, beta goes in the numerator. Alpha gets updated for n terms, alpha, alpha plus 1, etc. Same thing with beta, same thing for gamma in the denominator, Cn over n factorial. Now this is a classic, so this is the only relation I want to use. So this is a classic relation for hypergeometric that this also can be written in terms of this. So in terms of hypergeometric, this E R1, R2, so notice that k is a function of tau, of course. K is a function of tau. So this could be written as this, you see it as 3 by 2 plus 1, etc. up to n terms. So this will be n minus 1 here, n minus 1, and n minus 1. So notice that this is starting from 3. So if you want, we can write this as f of 3 by 2 comma 3 by 2, and here you have 1, 2, 3, etc. up to n. So that's going to be n. So this is going to be 1, and then k squared. K is a function of tau. That's this expression. You also have before that here, you have 2 sigma squared 1 minus k squared the whole squared f term. So we had 2 sigma squared 1 minus k squared the whole squared f of 3 by 2 comma 3 by 2. Now if you use this substitution, this can be written as f of, notice that gamma is here 1 minus 3 by 2, so this is minus half 1 k squared. And this, if I write it as a series, so this 1 minus k squared goes away because this is 1 minus k squared 1 minus 3 by 2 minus 3 by 2. So 1 minus 3 minus 2 cancels with this. So you end up just having 2 sigma squared here. Now if I substitute for the hypergeometric term here, multiplied by, let's notice that there is a pi by 4 here. So when you multiply by the pi by 4, this in fact becomes pi by 2. So with this, if I substitute for the f term, this becomes pi by 2 sigma squared summation n equal to 0 through infinity minus half plus 1 etc. minus half plus n minus 1. This twice because of this divided by n factorial k to the power 2n. Now notice that minus half plus half is half. So all the terms from here onwards is plus except the minus half term. So I could write this as pi by 2 sigma squared summation n equal to 0 through infinity minus half first term, then half, then 3 by 2 etc. Last term is 2n minus 3 over 2. This whole thing twice, so squared over n factorial k to the power 2n. If you want, we can, the same thing, we could also write this as notice that you have here 1, 3, for the next term will be 5 by 2, etc. So you have 1, 3, 5, etc. in the numerator up to 2n minus 3. And in the denominator, you have, if you take this, so you have here 2, then you take 2 into 2, you have 2 multiplied by 2. n factorial is of course 1, 2, 3, etc. So 2 into 2, then 2 into 3, so this is 2 multiplied by 3. etc. up to 2 multiplied by n. That also comes twice, so we can write it like this. And I'm going to add one term extra here, so this twice. So this is now going to read this way. There is a summation n equal to 0 through infinity of pi sigma squared over 2. Now this, if you want, you can expand this as pi sigma squared over 2. And if you just put n equal to 0, you get 1. Then the next term will be half squared k squared over 1. The next term will be 1 multiplied by 3 multiplied by 2 multiplied by 4 squared k4 over 3 squared, etc. In other words, the general term is of this form. Now I'm going to write, the interesting thing is I'm going to write this series in terms of the two elliptic integrals. And that's where we will, I showed the results earlier, but a bit more details. So if the two elliptic integrals are, the elliptic integral of the first kind is integral 0 to pi by 2, 1 over square root of 1 minus k squared sine squared theta d theta. And this is this one, in fact, it comes up in the pendulum, the swing of the pendulum. So the question is, how do you simplify this? Expand this as a binomial series and simply integrate it term by term. So I'm just going to sketch a couple of steps here. So this can be written as summation n equal to 0 through infinity, integral from 0 to pi by 2. If you expand it, minus half minus 1, etc. up to minus half minus n plus 1 over n factorial minus k squared sine squared theta to the power n. And there is an integral d theta. So if you, so remember that my integral 0 to pi by 2 sine squared n theta d theta it gets solved only for when n is even. And then if you substitute those results, this can be written as summation n equal to 0 through infinity 135 up to 2n minus 1 over 2n over n factorial. That's from here. Because you have minus 1 to the power n, minus 1 to the power n, so the minus cancels off. Then you have k to the power 2n. Then integral 0 to pi by 2 sine 2n by theta is 135, again 2n minus 1 over 2n n factorial multiplied by pi by 2. So if you put that up together, this is now going to read pi by 2 multiplied by summation n equal to 0 through infinity one, 3, 5, etc. 2n minus 1 over 2, 4, 6, etc. up to 2n, the whole squared, k to the power 2n. So this is for the elliptic integral of the first kind. And similarly, if you look at the elliptic integral of the second kind, so that's going to be integral 0 to pi by 2 square root of 1 minus k squared sine squared theta d theta. Go through the exactly the same expansion. For example, this will be n equal to 0 through infinity minus half plus 1, etc. minus half plus n minus 1 over n factorial. Then you have minus k squared sine squared theta to the power n d theta. Integral 0 to pi by 2. So this, if I pull this out, n equal to 0 to pi by 2, you have, I need to write 1 minus half, then, so this is minus half, this is going to be 3 by, this is going to be half, right? Minus half plus 1 is half. The next step is going to be 3 by 2, etc. Uh, 2n, you can see from here, 2n minus 2, 2n minus 3 there. And from the sign you get and here you have 2, 4, 6, etc. up to 2n. And you also have, you have to take care of the other terms, half, half plus 1. In other words, when you do the sine to the power 2n theta, you get 1, 3, 5, etc. 2n minus 1 over 2, 4, 6, etc. up to 2n, then pi by 2, and there is also a k to the power 2n. So the bottom line is, if you put this together, this now reads pi by 2 multiplied by 1 minus n equal to 1 through infinity, 1, 3, 5, etc., 2n minus 1, 2, 4, 6 up to 2n, the whole thing squared, k to the power 2n over 2n minus 1. So the important thing is to notice this minus sign. That's because, as I explained here, there is only one place the minus is going to come. So the minus sign will be there. And so what we have to look at this is now simply look at 2ek squared minus 1 minus k squared. This is the Uhlenbeck result. So we can substitute this summation here. We can substitute the k series into here, and if you simplify, you're going to get that step. So that's the final thing I want to show. So notice that for the elliptic integral of the second kind, this whole expression is going to come here. And elliptic integral of the first kind, we are going to take this expression and plug it in here. Then I'm going to show that what we get is this term, which would be the correlation between the two random variables. So let me so 2ek, so start from here. 2ek squared minus 1 minus k squared kk squared is pi by 2 So this now simplifies as pi by 2. 2 minus 1 is 1. So right now it's only a matter of putting the terms together. Then this is going to be minus 2 over 2n minus 1 plus 1 2n over 2n minus 1 the whole squared. But this is going to simplify as minus of 2n plus 1 right, over 2n minus 1 plus 2n squared over 2n minus 1 squared, and this thing is you can see here, so minus 4 n squared minus 1 in the numerator plus 4n squared over 2n minus 1 the whole squared, so that which turns out to be 1 over 2n minus 1 the whole squared. So in other words, this now reads pi by 2 multiplied by 1 plus summation n equal to 1 through infinity 1, 3, 5 up to 2n minus 1, 2, 4, 6 up to 2n the whole squared, k squared tau over 2n minus 1 the whole squared from here. And if you look at that, that's exactly this expression. Pi by 2 sigma squared 135 2n minus right, so 135 up to 2n minus 1, the whole squared, there is a whole squared there, to Right, so if you want this also, we can write as pi by 2 sigma squared summation n equal to 0 through infinity 1, 3, 5 up to 2n minus 1, 2, 4, 6 up to 2n the whole squared over k squared tau over 2n minus 1 the whole squared. Same expression as this. That's exactly this expression, except I forgot to bring up this square here. So consequently, we get this thing to be so this is going to be, so you have a sigma squared there, so this is E R1 R2 over sigma squared, or E R1 R2 is, so we get this expression, this multiplied by sigma squared is equal to E R1 R2. So here is the summary. If you start with the two, if you take two time instants from a jointly Gaussian process, each of the amplitudes are Rayleigh, but their joint density function is given by this expression, and their correlation coefficients can be expressed either as an infinite power series or in terms of the elliptic integrals of the first and second kind, and this result is due to Uhlenbeck and goes back to I think about 1948 or so. Uhlenbeck is the, I think he worked in the Manhattan project, and after that was over, I think he must have started working on this integral.